Today, I'm going to tell you one of the most intriguing stories in the history of science. Our story begins in the 18th century. On March 13, 1781, the great astronomer William Herschel discovered Uranus, the seventh planet of the solar system. But Uranus was unusual. In the 19th century, calculations showed that Uranus's orbit didn't match Newtonian physics. Specifically, its ecliptic longitude, which is its position within the plane of the solar system, and its radius vector, which is its distance from the Sun, displayed anomalies that Newton's physics couldn't explain. At that time, Newton's theory of gravity was well established. It explained the motion of moons around planets and planets around the Sun perfectly. This success gave physicists great confidence. They could predict the orbits and velocities of almost any object just by using Newton's equations. But Uranus disrupted everything. This left two possibilities. One was that Newton's theory had limits. Maybe, when you went far enough from the Sun, Newton's laws began to break down. After all, no one had tested Newton's formulas at such great distances. Perhaps the theory wasn't truly universal, and we had finally reached its boundaries. This mystery posed a big question for scientists. The second possibility was that, at that point, the theory we had been using for over a century, explaining every motion of every celestial body with absolute success, was correct. However, we, as observers, had missed something. Perhaps there was another planet that we had yet to detect, and it was applying immense gravitational forces on Uranus, shifting its orbit in ways we hadn't expected. The French astronomer Urbain Le Verrier believed that the second possibility was true. So, he set about calculating how far away and how large this celestial body, which could cause anomalies in Uranus's orbit, would have to be. Think about it. This calculation was extremely difficult, especially in the 1800s. No computers, not even the technology we have today. It's even more astonishing when you consider that Newton's physics could easily calculate the gravitational pull of a given mass, but when it came to figuring out where and how large a celestial body causing this gravitational pull might be, the problem became far more complex. There could be many different masses and distances that would produce the same gravitational effect. In fact, multiple bodies could be exerting their influence at the same time, creating the observed pull. But he succeeded. Le Verrier, along with John Crouch Adams, who was completely unaware of Le Verrier's work, calculated in 1845 the size and position of a planet that could explain the anomalies in Uranus's orbit. These entirely mathematical calculations were initially ignored by astronomers. Nevertheless, Le Verrier persistently sent his results to observatories with the necessary telescopes, and as a result, the observational testing of his calculations took a year. Finally, Johann Gottfried Galle, an astronomer at the Berlin Observatory, Urbain Le Verrier calculations. He asked Le Verrier a few questions, and after some adjustments, Le Verrier sent back the revised calculations. On September 23, 1846, the day Galle received the final version of Le Verrier's calculations, he aimed the observatory's telescope at the location Le Verrier had predicted. Within less than an hour, Galle found Neptune, almost as if it had been placed there. Le Verrier's theoretical calculation was so accurate that Galle found Neptune just 1 degree away from where Le Verrier had predicted. To give you a sense of scale, 1 degree is about the width of your little finger when you stretch your arm out. And just like that, the 8th planet of our solar system, Neptune, was discovered. Do you see the importance of what was done here? We develop a theory that explains the motions of objects around us. Newton's theory of gravitation. Using this theory, we can describe the behavior of countless newly discovered celestial bodies the moment we observe them. This is why, when one of these objects seems not to fit the theory, we don't immediately abandon it. Instead, we double-check our observations because the theory makes testable and falsifiable predictions about the cause of that anomaly. It says, if X exists, then Y can be explained. We search for X, and we find it exactly where the theory predicted, in the exact manner and size it anticipated. This is the triumph of science. This is the power of science. If such a powerful method doesn't make you sit back in awe, I don't know what will. But wait, our story doesn't end here. Let's move now from the outer edges of the solar system to its very center, Mercury. In the 19th century, astronomers studying Mercury, the planet closest to the Sun, noticed something peculiar about its orbit. One of those astronomers, once again, was Verrier. Mercury, which is about 1/3 the size of Earth, exhibited anomalies in its orbit. As planets approach their closest point to the Sun, known as perihelion, their elliptical orbits shift slightly over time. This is called perihelion precession. The cause? Other planets' gravitational forces, the Sun's slight bulge, and other factors that perturb the orbit. Newtonian physics could easily explain all of this, but Verrier discovered that Mercury's orbit displayed an additional anomaly, an unexplained precession of 43 arcseconds per century. To put that in perspective, an arcsecond is just 1/84th the width of your pinky finger held at arm's length against the sky. It's an incredibly tiny deviation, yet it was unmistakably real. And Newtonian physics could not account for it. This time, however, astronomers were confident. They had been through this before and knew what to do. Questioning Newton's theory didn't even cross their minds. Instead, they proposed that an unseen planet was pulling Mercury slightly off course. The reasoning was simple. This hypothetical planet must be so close to the Sun that it had evaded detection until now. Astronomers were so sure of its existence that they even gave it a name before finding it: Vulcan. The search began immediately. Calculations were made, and the position and size of this so-called zeroth planet that could explain the anomaly were determined. But there was a small problem. No matter where they looked, they couldn't find Vulcan. It simply wasn't there. They tried everything. Countless astronomers scanned the Sun's surroundings with their telescopes. Nothing. They looked for the dark spot Vulcan should have created as it passed in front of the Sun. Still, nothing. During total solar eclipses, when the Sun's brightness dimmed, they hoped to spot the elusive planet near its edges. But again, nothing. Tensions began to rise. Could it be that Newton was wrong? In 1915, Albert Einstein presented his theory of general relativity. Interestingly, this groundbreaking theory had nothing to do with Mercury at first. Einstein wasn't trying to solve Mercury's orbital anomaly. Instead, he had a fundamentally different idea about the nature of gravity. According to Einstein, gravity wasn't an invisible force acting along a string between two objects, as Newton had described. Instead, massive objects warped the fabric of space-time itself, and these warps influenced the straight-line motion of objects, pulling them into orbits. This model, Einstein argued, explained the nature of gravity far better than Newton's. And it turned out that this new framework held the key to understanding Mercury's orbital anomaly. If you're very close to a massive object, like the Sun, Newton's orbital predictions begin to break down. Newton's theory didn't account for the effects caused by the warping of space-time. He had never even considered such a warping. But when we calculate Mercury's orbit, taking into account the warping of space-time caused by the Sun's immense mass, the theoretical results perfectly match what we observe through our telescopes. Mercury's orbit aligns precisely with the predictions of Einstein's general theory of relativity, a more expansive and accurate theory of gravity. This new theory didn't just explain Mercury's orbit. It explained everything Newton's theory could, and much more. And on that day, the idea of Vulcan died. Science had seemingly put an end to the discussion. But wait, it wasn't over yet. Remember Neptune, the planet discovered thanks to the anomalies in Uranus's orbit? While all these events surrounding Mercury were unfolding, some astronomers continued to observe Neptune's orbit. After all, Neptune had not yet completed a single revolution around the Sun since its discovery. Today, we know that a year on Neptune lasts 165 Earth years. By the mid-20th century, astronomers still didn't have a complete picture of Neptune's orbit. They only knew fragments of it. And within those fragments, they discovered something intriguing. Neptune's orbit also had a problem. Here's the issue. Using Neptune's current position, you could calculate where it should be weeks or months into the future using Newtonian physics. But Neptune wasn't exactly where it was supposed to be. Newton's theory wasn't working here either. Moreover, while Neptune's existence explained almost all the orbital anomalies observed in Uranus, it couldn't account for every single one. This time, Einstein's theory wasn't the answer. Neptune is located in the farthest reaches of the solar system, where the Sun's gravitational pull is so weak that Einstein's theory doesn't offer any additional insights. In such cases, Newton's and Einstein's theories yield identical results. That's precisely why we still use Newton's theory to build cars, airplanes, and houses. Einstein's theory didn't disprove Newton's. It expanded the scope and precision of Newton's framework. So, what now? Astronomers return to their starting point. There must be a ninth planet, they concluded. But this time, they were more cautious. Instead of giving it a flashy name, they simply called it planetX, meaning the unknown planet. During this period, many set their sights on discovering this mysterious planet X. One of them was Percival Lowell, a wealthy businessman and astronomy enthusiast who was particularly obsessed with finding life on Mars, if it existed. Driven by his passion to become the one who discovered Planet X, Lowell built an observatory from scratch, the Lowell Observatory, which still operates in Arizona today, scanning the skies. Unfortunately, Lowell passed away in 1916, before he could witness the discovery of Planet X. Following his death, the observatory paused the search for a while. Then came 1928, when a young man from Kansas named Clyde Tombaugh, who lacked formal high school education but had an immense passion for astronomy, submitted incredibly detailed hand-drawn sketches of Jupiter and Mars. At that point, the head of the Lowell Observatory, the renowned astronomer Vesto Slipher, was so impressed by the drawings that he immediately invited Tombaugh to the observatory and hired him on the spot. In 1929, the team resumed their search for Planet X. Tombaugh, as his intricate drawings suggested, was meticulous and extremely dedicated to his work. At regular intervals, he pointed the observatory's telescope toward regions of the sky where they believed Planet X could be, capturing precise photographs of the heavens. Using the blink comparator method, they compared photographs of the same part of the sky taken at different times. Distant background stars, which hardly moved, served as a stationary backdrop. If a planet happened to pass in front of those stars, it would appear to move in the images. Of course, this required the team to take photos at just the right time, in just the right place, with enough precision. And Tombaugh was so meticulous that just a few months into the job, on February 18, 1930, he discovered the ninth planet, Pluto. But there was a catch. Initially, Pluto was thought to be about the size of Earth, which seemed to explain the orbital anomalies of Neptune and Uranus. However, later it was revealed that Pluto wasn't just smaller than Earth, it was smaller than the Moon. This meant that Pluto couldn't possibly affect Neptune's orbit. What we thought we'd discovered, the elusive Planet X, wasn't the planet we were looking for. Naturally, this sparked a wave of myths in popular culture. Some claimed the anomalies were caused by aliens. Others dreamed up outlandish theories about celestial bodies like Marduk. Even Tombaugh, later in his life, admitted to having an interest in extraterrestrials, which only fueled these speculations. But Pluto didn't need any of that. Even though it couldn't solve Neptune's orbital mysteries, Pluto was one of the most remarkable discoveries in the history of science. If you like this type of videos, you can like, subscribe, and comment for more. Years passed, bringing us to 1993. By then, no Planet X had been found, and no explanation for Neptune's orbital anomalies had emerged. That's when Miles Standish from NASA's Jet Propulsion Laboratory decided to take one last approach, re-evaluating the data for Neptune's orbit. Where do we even get data on a planet like Neptune, you might wonder? Over centuries, observatories around the world have carefully recorded celestial objects' movements and shared this data with theorists who then test their hypotheses. Standish examined these records, focusing on Uranus's orbital data between 1895 and 1905, which had come from the United States Naval Observatory. He noticed a peculiar pattern in the anomalies that suggested a calibration issue with their telescope. He asked himself, what if we temporarily ignore these questionable observations and only rely on data from other observatories? When he did this, the errors in Neptune's orbit decreased dramatically, but not entirely. Later, when Voyager 2 made its flyby of Neptune, it provided far more precise measurements. Using this new data, Standish discovered that Neptune's mass had been overestimated by 0.5%. When he factored in this updated mass, Neptune's orbit had been perfectly consistent with Newton's theory all along. This time, the problem wasn't with the theory or a missing planet. It was with our observational tools and how we processed the data. Nature hadn't misled us, our telescopes and methods had. In the end, there was never any need for a Planet X. All 8 planets' orbits could now be explained flawlessly.